Something strange is happening. Not the kind of strange that meteorologists wave off as a minor anomaly. Not the kind of strange that gets buried in the technical footnotes of a forecast discussion. The kind of strange that makes experienced, decorated, decades, hardened hurricane scientists stop mid-sentence and say, and these are their actual words, not dramatization, that they are looking at a screwball season, a hard year to characterize, simply odd. Get ready. Because when the people who have dedicated their entire professional lives to understanding these storms start using words like bizarre, unpredictable, and thoroughly weird, the rest of us need to sit down and listen carefully. This storm just took a strange turn. And the strangest part is that strange turns are becoming the new normal. Stay alert, because before we go any further, you need to understand something that almost nobody tells you when they talk about hurricanes and tropical storms. Most people imagine these storms as predictable forces of nature. Big, yes. Dangerous, absolutely. But understandable. Systems that follow rules, move in expected directions, behave according to known patterns. You track them on a map, watch the cone of uncertainty, and make your decisions accordingly. That model of how storms behave is increasingly dangerously wrong. The storms forming today are not following the rules. They are breaking them in ways that are shocking researchers, defeating forecast models, and creating the exact kind of deadly surprises that kill people who thought they had time to act. Let us start with the 2025 Atlantic hurricane season, because it is a masterclass in strange. When atmospheric scientist Phil Klotzbach at Colorado State University, one of the most respected hurricane researchers on the planet, described the 2025 season as screwball. That was not casual commentary. That was a scientist confronting data that defied almost every prior expectation. Here is what happened. The season produced only 13 named storms below what had been forecast, below average in number. That should mean a quiet, relatively safe year. That is what people hear when they hear below average. Safety, relief, a season to breathe through. What actually happened was something nobody was fully prepared for. Fewer storms formed, but the storms that did form skipped moderation entirely and went straight to catastrophic. 3 separate hurricanes reached Category 5 intensity, 3 in a single season. The only other time in recorded history that happened was 2005, which stands as one of the most destructive hurricane seasons ever documented. And there was one, just one, moderate Category 1, 2, or 3 hurricane in all of 2025. One storm out of 13 fell into what used to be the most common range of hurricane strength. The rest either stayed as tropical storms or exploded directly to Category 4 and 5. The middle of the hurricane intensity scale is disappearing, and when researchers analyzed why, the explanation was simultaneously elegant and terrifying. The ocean is now so warm, so deep with heat, energy, that storms no longer plateau at moderate strength. They either get capped by hostile atmospheric conditions as tropical storms, or they find a window of favorable conditions and instantly launch toward maximum possible intensity. There is no gradual middle anymore. Stay alert, because that strange disappearance of moderate hurricanes is just the beginning of what made 2025 so unsettling. The season also featured one of the most mystifying atmospheric pauses in recorded meteorological history. During the first half of September, the climatological peak of hurricane season, the window when conditions are historically most favorable for storm development, there was nearly 3 weeks of complete inactivity. No named storms. Nothing. The atmosphere went eerily, inexplicably quiet at the exact moment it should have been most active. Researchers at the University of Cambridge, analyzing the season afterward, identified the mechanism: a persistent upper-level trough, suppressed African easterly waves, and dry air anomalies that shut down development. But even understanding the mechanism after the fact does not erase the strangeness of the experience in real time, when forecasters were watching an anomalously warm ocean sit silent and storm-free during the peak of hurricane season, knowing that somewhere beneath that calm surface, the fuel for something catastrophic was accumulating. And then the season woke up, violently. The late season of 2025 was where the truly strange things happened. Hurricane Melissa formed in October and became the strongest storm to ever make landfall in Jamaica, arriving with sustained winds of 185 miles per hour and a central pressure of 892 millibars, the third lowest pressure ever recorded in an Atlantic hurricane. Its name was permanently retired by the World Meteorological Organization, erased from the list of Atlantic storm names that rotates every 6 years, never to be used again, because the storm it named was too catastrophic to associate with any future weather system. Scientists who analyzed Melissa's structure afterward noted something that belongs in the chapter of Textbooks on strange storm behavior, the way it interacted with Jamaica's mountainous terrain while maintaining Category 5 intensity, was unlike anything in the research record for that region. Intense tropical cyclones have higher inertial stability, more compact wind, fields, and shallower boundary layers that cause them to respond to terrain interactions in fundamentally different ways than weaker storms. Melissa was so intense, so compact, so powerful at landfall, that its behavior over Jamaican terrain produced structural dynamics that researchers are still trying to fully characterize. Stay alert, because the Fujiwara effect is not a theoretical curiosity from old research papers. It happened in 2025. Hurricanes Imelda and Humberto entered a Fujiwara interaction in the Atlantic, one of the only times this rare event has occurred in that basin. The interaction caused Imelda's forecast track to swing dramatically eastward within 3 days, sending meteorologists scrambling to update their models. Communities that had been preparing for a direct hit were suddenly taken out of the path. Communities that had felt safely distant were suddenly in the cone. When two storms begin the Fujiwara dance, every forecast made before the interaction started becomes unreliable, and the window of time available to make new safety decisions shrinks drastically. Get ready, because here is something even stranger that most people have never been told. You know the rule about hurricanes weakening over land. Everyone knows that rule. A storm makes landfall. It loses its connection to warm ocean water. It weakens. It is practically the first thing anyone learns about how hurricanes work. You move inland, you are safer. You get past the coast, the worst is over. This rule is true in most cases, but there is a documented, scientifically verified phenomenon that turns this assumption completely upside down, and it is called the brown ocean effect. The brown ocean effect occurs when a tropical storm or hurricane that has moved over land encounters soil that is so saturated with water, from previous flooding, heavy rainfall, or exceptionally high moisture content, that the waterlogged ground begins to behave like a warm ocean surface. The soaked earth releases heat and water vapor into the atmosphere above the storm, just as a warm ocean would, feeding the storm's convective engine and allowing it to maintain strength or even intensify despite being hundreds of miles from the coast. The discovery of the brown ocean effect emerged directly from one of the strangest storm evolutions in American meteorological history. Tropical Storm Erin in 2007 was weak, disorganized, and barely worth tracking when it made landfall. Meteorologists gave it little attention. It moved inland across Texas and appeared to be dying, as inland moving tropical systems do. And then, something that should not have happened. Erin encountered the exceptionally waterlogged soils of Oklahoma, soaked by heavy seasonal rains, and instead of continuing to weaken, it began to strengthen. Not just maintain, strengthen. It developed an eye, an actual, clear, defined eye. A storm that was supposed to be fading into a remnant low in the middle of the continent developed a feature that only occurs in genuinely powerful tropical cyclones over the grasslands of Oklahoma. Scientists studying the satellite imagery afterward were stunned. Research funded by NASA subsequently confirmed that this was not a fluke, but a reproducible physical mechanism, and that at least a dozen storms between 1997 and 2008 had been affected by it to varying degrees. Stay alert, because the brown ocean effect has implications that are genuinely alarming for the future of storm preparedness. As climate change increases the frequency and intensity of rainfall events across the continental interior, and as back-to-back, storms create cumulative soil moisture conditions that persist for weeks. The conditions for the brown ocean effect become more common. A storm that weakens at the coast, a storm that residents 300 miles inland believe they have escaped, may find the fuel it needs to re-strengthen oversaturated farmland. The rule that told those inland residents they were safe is not a reliable rule anymore. And while all of this is happening, another strange reversal is unfolding beneath the ocean's surface. Storms are heat engines. They pull energy from warm water. But what almost nobody discusses is that a slow-moving hurricane can actually destroy its own fuel supply. As a storm moves over the ocean, its rotating winds and low-pressure center generate a process called upwelling, pulling cold water from depths of 165 to 330 feet up to the surface. If the storm moves quickly, it outpaces the cold water it brings to the surface and keeps feeding on the warm water ahead. But if it slows down, stalls, or turns back on itself, it begins to churn the cold water it has upwelled directly into its own fuel supply, essentially cooling the ocean beneath it and starving itself of energy. A 1 to 2 degrees Celsius drop in sea surface temperature beneath a hurricane is the difference between a Category 4 and a Category 1. The storm literally erodes the conditions that are sustaining it. And yet, even as this self-destruction is happening, the storm can re-strengthen the moment it moves over warmer water, producing the bizarre, terrifying pattern of a storm that weakens, lulls communities into reduced alert, and then explodes back to major intensity before landfall. This exact pattern happened with Hurricane Ivan in 2004, which executed a full loop in the Gulf of Mexico, one of the strangest tracks ever recorded in Atlantic hurricane history. Ivan made landfall, weakened over land, reformed in the Gulf of Mexico as a tropical system, and threatened coastal communities a second time. Ivan's track was so bizarre, so looping and unpredictable, that it became a standard teaching example of how strange storm paths can get when the steering currents that normally push systems along their tracks collapse or change direction. Get ready, because the steering current collapse is one of the most dangerous strangenesses of modern storms, and it is becoming more common. Hurricanes and tropical storms are steered across the ocean by large-scale atmospheric wind patterns, the same jet stream and high pressure, systems that determine the weather across entire continents. When those steering currents are strong and well-defined, a storm moves briskly along a predictable path. Forecasters can track it with reasonable confidence, days in advance. People have time to prepare and evacuate. But when the steering currents weaken, when the jet stream becomes sluggish, meandering, or disrupted, a storm can become what meteorologists call a stalled or quasi-stationary system, and a stalled storm is a nightmare in ways that go far beyond what its wind speed suggests. Hurricane Harvey in 2017 is the most devastating example in American memory. Harvey made landfall as a Category 4 hurricane, which was catastrophic on its own. But what made Harvey a defining catastrophe of the modern era was what happened next. The storm stalled. It sat over Houston, Texas for 4 days, barely moving, held in place by a collapse of the atmospheric steering pattern above it. During those 4 days, it dropped over 60 inches of rain on parts of the Houston metropolitan area, the largest rainfall total ever recorded from a tropical cyclone in United States history. The flooding it caused was not from storm surge. It was not from hurricane-force winds. It was from water. Just water, falling endlessly from a sky that showed no signs of moving on. The flooding reached into neighborhoods that had never flooded in 100 years of record-keeping. It reached highways, office buildings, hospitals, and neighborhoods 20, 30, 40 miles from where the storm made landfall. 103 people died, $125 billion in damage. And Harvey was, at the moment of its worst flooding, no longer even a hurricane. It was a tropical storm that could not figure out where to go. Stay alert, because the jet stream disruption that caused Harvey's stall is not a once-in-a-generation event. Climate scientists analyzing atmospheric patterns confirm that the jet stream has been behaving more erratically, weakening and meandering more dramatically as the temperature difference between the Arctic and the mid-latitudes narrows due to global warming. That narrowing reduces the energy gradient that keeps the jet stream fast and steady. The result is a slower, more wavering jet stream that is more likely to get stuck in blocking patterns. And a stuck jet stream is a storm stalling machine. In the summer of 2025, the polar jet stream shifted unusually far south and weakened, stalling storm systems across the mid-latitudes OF the United States, causing prolonged flash flooding episodes and keeping weather systems locked in place far longer than their historical counterparts. The atmosphere is changing in ways that make the steering environment for storms less predictable and more prone to the kind of collapse that turned Harvey from a one-day wind event into a 4-day water catastrophe. Get ready, because the Eyewall replacement cycle is another strange, little understood behavior of major hurricanes that can produce bewildering changes in intensity at the worst possible moments. When a hurricane reaches major strength, Category 3 and above, its inner core can sometimes begin to develop a second eyewall that forms in a ring around the original. The two eyewalls then compete for energy, with the outer one gradually strangling the inner one. During this process, the storm typically weakens as the original eyewall collapses. Then, as the outer eyewall consolidates and contracts, the storm can re-intensify, often to a new and higher peak. For people watching the storm from outside, this process looks like the storm inexplicably weakening and then roaring back. For forecasters, it is a genuine challenge because the timing of each phase of the cycle is difficult to predict with precision. A storm that the forecast said would weaken before landfall can undergo eyewall replacement and arrive stronger than expected. During the 2025 season, Hurricane Humberto was undergoing an eyewall replacement cycle. At the same time, it was interacting with the remnants of the Fujiwara dance with Imelda, producing a situation of compounding strangeness that tested the limits of real-time forecast accuracy. Stay alert and understand why all of this matters for the season that is now beginning. The 2026 Atlantic hurricane season opens on June 1st, but storms do not wait for calendar dates. Earlier in 2026, Super Typhoon Senlaku in the Pacific demonstrated exactly how strange and explosive storm behavior can be in this era of record ocean heat. Senlaku began as an ordinary tropical storm. Within 36 hours, it had intensified by 75 miles per hour. more than double the threshold that defines rapid intensification, and was roaring toward the northern Mariana Islands as a Category 5 typhoon with 180-mile-per-hour winds. The ocean beneath it had warm water extending to great depth, heat, content of 125 to 150 kilojoules per square centimeter. That is not a surface layer of warmth that a storm can deplete. That is a column of energy so deep that the storm can churn up well and still find warm fuel underneath. The 2026 season is being watched with intense anxiety by forecasters, not because the storm count is expected to be particularly high, but because the ocean heat content underlying whatever storms do form is extraordinary. AccuWeather's lead hurricane expert confirmed that forecasters are very concerned about rapid intensification, very similar to the last couple of years, and that the concern stems not from surface temperatures alone, but from the depth of warmth, water that is exceptionally warm hundreds of feet below the surface across most of the hurricane basin. When a storm finds that kind of deep fuel, the strange turns happen faster, hit harder, and leave less time for anyone to respond. Get ready and recognize that the strangeness of these storms is not just meteorologically interesting, it is operationally lethal. Stay alert because the forecasters watching the 2026 season are not being alarmist when they say that even a below-average season can produce historic disasters. They are being precise. In 1992, only 7 storms were named in the Atlantic. Andrew was one of them. Andrew made landfall in Florida as a Category 5 hurricane, leveled the city of Homestead, and forced a complete rethinking of building codes, insurance structures, and storm preparedness across the entire American coastline. The number of storms in a season is a statistic. The storm that hits your neighborhood is an event. And events, as 2025 and every season before it have proven, do not conform to statistics. The 2025 season ended with the scientific community publishing one remarkable, sobering conclusion after another. Moderate hurricanes are disappearing. Category 5 storms are multiplying. Rapid intensification events have tripled since 1980. The jet stream is weakening. Ocean heat content is at record depths, the brown ocean. Effect is becoming more likely as inland flooding events increase. The Fujiwara effect will keep defying track forecasts when conditions bring 2 storms close enough to dance. Eyewall replacement cycles will keep producing the sudden reversals that catch communities off guard. And the storms that form under these conditions will keep taking strange turns. Turns that defeat the models, turns that betray the assumptions, turns that move faster than evacuation timelines allow. Get ready. The strange turn is not a one-time event. It is the defining characteristic of this era of tropical weather. It is what happens when record ocean heat meets an increasingly disrupted atmosphere and creates storms that learn the old rules and then decided to break every single one of them. Know your zone. Know your route. Know that the calm before a storm is not a signal that the storm is less dangerous. Sometimes it is the eye. Sometimes it is the lull before a storm doubles back. Sometimes it is the quiet of a steering current about to collapse. And sometimes it is the last few hours before a storm that looked manageable on last night's forecast takes a strange turn and becomes something no forecast said it would be. Stay alert. The ocean is warm, the atmosphere is loaded, and this storm just took a strange turn.